This is 512 rectangular approximation method, or RAM. We have three new definitions in this subsection: MRAM, LRAM, and RRAM. Those are all abbreviations, obviously, and no new rules or theorems. Let's get to it and find out quickly what MRAM, LRAM, and RRAM are. So when we studied derivatives, we started with the derivative or rate of change at a point. Good place to start, always at one place. This led to the derivative function later on, a function that tells us the value of the derivative at any point. So we started out with the limit definition of derivative. It gave us the slope of the curve at one particular point. Quickly, we found out, though, that it was going to be important for us to know what the derivative was at many, or really any point on a function. And that's how we developed the limit definition of derivative function and all of our derivative rules from there. Well, that same idea applies to accumulation. In example 2 that we did in the previous video, we specified that we wanted to accumulate distances up to a particular time, kind of like derivative at a particular point. Later on in this chapter, we're going to study the accumulator function, which is going to be a function of t that tells us just how much has accumulated up to any value of time. So we could ask a question like, what is the total distance traveled by a ship on the ocean at any given time? What is the total amount of snow accumulated at any given time? And that's a much more interesting question than just at one particular time. But along this path and to get there, this section, we're going to talk about some new terminology to make these area approximations a bit easier. So in that example that we just referenced, example 2, we used what's called midpoint rectangular approximation method, MRAM. We used the MRAM to approximate the area under the curve. Why that name? Well, I think that name suggests that when we made our choice for the height of each of those rectangles, we were choosing the height by taking the midpoint of each subinterval. As a reminder, we were trying to find the area under a curve. We had sliced that curve into separate strips, and we were going to find area of rectangles that were made by those strips. And we thought, well, how do we find the height? And what we did was go inside of each subinterval and find the height that way. So there was a little bit of an over and underestimate each time. We also could have done that two other ways. We could have used just the left side of subintervals, and that would have been LRAM, or left-hand rectangular approximation method. And we could have used just the right side of the subintervals, which would have been RRAM, or right-hand rectangular approximation method. So this graphic gives us an idea about what each of those scenarios look like. It shows you those three approximation methods and graphically what you're doing if you're trying to find the area under the curve y equals x squared, starting at x equals 0, going to x equals 3, and using 6 subintervals. So let's take a look. In the first image, we'll call this one number 1. We have, starting at 0, here's 1, here's 2, there's 3. We've diced up or sliced up 0 to 3 into 6 subintervals. So 0 to a half to 1, 1 to 3 halves to 2, and 2 to 5 halves, and 5 halves to 3. Then when we drew in graphically the rectangles, we were finding the height of each of those rectangles by taking a look at the left side of each of those subintervals, going up to the curve, and then using that as the height. So let's start at the right side, because I think it's easier to look at there with a larger rectangle. Here's your subinterval from 5 halves to 3. Here's the left side at 5 halves. Go up to the curve, and whatever that y value is there, that's the height of the rectangle. And you can kind of continue on down and draw it there. Then we go to the next one. This is the subinterval between 2 and 5 halves. We can go up to the curve. That's the new height, and then over, and you have your second, and then you can continue this path, and we can see that the last subinterval, or the first one, I suppose, if you started all the way over at the left, actually is not a rectangle at all. It has a height of 0. I still like to draw it in so that we see there's something there, but it has a base of 1/2 and a height of 0, since the y value on the left-hand side of that subinterval was 0. Then we'll call this one 2, and we'll call this one 3. I think let's go to 3 next, because this is very similar. It's the same 0 to 3 on the x-axis interval that's divided up into 6 subintervals, but this time the height comes from the right side. So you look between 0 and 1/2, and we say, okay, the right side of that subinterval is 1/2, up to the curve, over. It's a very short rectangle, but it's there. And then we continue that on. We use those right sides, we go up to the curve, and notice these rectangles are looking like they're just living a little bit over the curve. So if we added all of those rectangles up, we might get an area approximation that's a bit more than what the actual area is. And then finally, number 2, this is your MRAM. This is the midpoint rectangular area approximation, or rectangular approximation method, because look at the heights here. Yes, we still start from 0. We go to 1. Here's 2. There's our 3. We have our subintervals of 1/2 and 3/2 and 5/2. But the height of each of these rectangles was not drawn from the left or right sides of the subinterval. It was actually drawn from the middle. And you can see that here between 5/2 and 3. We take a look at the number in between those, and we can move up to the top of the curve. And now, instead of going over left or over right, you do both. And that is how you get your height. And you can probably start to get an idea that MRAM might give a better approximation, because there's not as much of an underestimate like there is in LRAM, and there's not as much of an overestimate like there is in RRAM. And actually, the LRAM and RRAM over and under approximations kind of cancel out with MRAM. So that's kind of a good thing. And here's the middle. There's your midpoint. Go up to the curve, over, and back down. And so that's how you take your heights, or find your heights of the rectangles in MRAM. So let's label these. Here we have LRAM, here we have MRAM, and here we have RRAM. So I tell you what, let's find the areas now. Yeah, let's find the areas. No matter which RAM we compute, we are adding products of the form, oh gosh, there's some math symbols, f of x sub I times delta x, or in this case, x sub I squared times 3/6. Oh, there's a lot to unpack here. It's a good thing we've got some white space. Let's talk about delta x first. Delta x is the length of a subinterval. I'm going to write this up here. Delta x is the length of a subinterval. And you find that length of a subinterval in a pretty standard way. It's one I think you're going to be used to. Basically, do this. Subtract the end of the whole entire interval from the beginning, or actually it's the beginning from the end, b minus a, and then divide that by how many rectangles in. So what this is telling us then is that we start at x equals a, end at x equals b, and we have n rectangles. So that's your delta x, and it's why we've replaced delta x in the second line here with 3/6, because in this example from the previous slide, we started at 0, we went to 3, and we had 6 subintervals. So let's see what that would look like. Delta x then would be 3, there's your ending point, minus 0, there's your beginning point, divided by 6 rectangles. So this is 3/6, and that actually becomes then 1/2. So what about the f of x sub I? Well, x sub I stands for your index. This is either the left side or right side or midpoint as you move from 0 to 3. So if we go back to this previous slide, I'm going to come in here in green now. When we're doing our left-hand rectangular approximation method, our x sub i's would be 0, there's x sub 1, and then 1/2, there's x sub 2, and then 1, there's x sub 3. And then you plug those numbers into f, into the function itself, to find the heights. So that's why we've replaced f of x sub I with x sub I squared, because remember the graph we were using was y equals x squared, or f of x equals x squared. So let's see what these areas actually look like. So for the left-hand rectangular approximation method, we're going to look back here and start adding up the areas. So the first rectangle, that's this one that didn't really have a height at all. That's going to be this, height of 0, there's a bell, times the width of that rectangle, which is 1/2. And then we go to the second one. So here the height is taken by using the index 1/2 and plugging that into the function and then multiplying by the height. So this one is, or by the base. So this one's 1/2 squared times 1/2. And then the third rectangle would be from the 1. So we go up there and over. So this is 1 squared times 1/2. So there's your first 3 rectangles. And then we're going to add in the next one. After 1, the index was 3/2. So 3/2 squared times 1/2. Plus the next one was 2 squared times 1/2. Plus the next one after 2 was 5/2. Plug it into the function squared. There's your height times the base, 1/2. And there's 1, 2, 3, 4, 5, 6. There's all 6 of the rectangles. And if we add those together, we end up with 6.875. Let's do the right rectangular approximation method next. We'll go to RAM, and so we're looking at the third graphic over here. The widths of all the rectangles stay the same. However, the only change comes in with the indices. Now we're using right hands of the subintervals to get the height of the rectangle. So we're going to begin with 1/2 and then move to 1 and then 3/2 and then 2 and then 5/2 and then 3. So the difference here is that we will not use 0 as an index. We will use 3. So let's get back over here. We'll go in with the first one, which is 1/2 squared times 1/2 plus 1 squared times 1/2 plus 3/2 squared times 1/2 plus 2 squared times 1/2 plus, where are we at, 5/2 squared times 1/2 plus one more. Oh, right, that was 3 squared times 1/2. And this one comes out to be 11.375. So at this point, we know from the graph that our LRAM is an underestimate and our RRAM is an overestimate. So here I'm just going to make a note. This is under, this one's over. And we're guessing now the area under x squared from 0 to 3 is somewhere between 6.8 and 11.3. MRAM might give us a better idea. So MRAM is the one that's slightly different than the other two, right? Because even though the width of every subinterval stays the same, we get the height differently. We have to look at the midpoint. So here's what we're going to do in the MRAM diagram here. What is right in between 0 and 1/2? Well, that's 1/4. And what's in between 1/2 and 1? That's 3/4. And these are the indices that we'll use to plug into the function y equals x squared to get the height. So 1/4, 3/4. Here's 5/4 and 7/4 and 9/4 and 11/4. So those are the 6 indices we'll use for those rectangles. And let's go to the next slide and get that in. So the first one's 1/4. We'll square it, we'll multiply by 1/2. And then what was next? 3/4, and we'll square it and multiply by 1/2. And then 5/4 and square it and multiply by 1/2. And then 7/4 and square it and multiply it by 1/2. And then 9/4 and square it and multiply by a half. And finally, 11/4 and square it and multiply by a half. And this turns out to be 8.9375, a much, much better approximation of the area. We knew it was somewhere between 6.8 and 11.3. Well, 8.9 is kind of right in the middle of those two. And I'm going to refer you to, here it is, the graph on the next slide. Notice what happens now. Now, we started with 6 rectangles. I'm going to write that here, rectangles, or we'll call them subintervals. Now, we know that LRAM was smaller than the true area, and LRAM is smaller, and RRAM is larger, and MRAM was the best fit. But watch what happens when we increase the number of rectangles. When we go to 6 rectangles, LRAM gets a little bit bigger, MRAM gets a little bit smaller. We go to 24, so we're doubling the number of rectangles. Now, LRAM gets a bit bigger, and RRAM gets a bit smaller. MRAM just seems to be kind of perfecting itself. Then we double it again, we get to 100, we get to 1,000. Now look how close these 3 approximations are. 8.986, 8.999, 9.013. They all seem to be converging on the same number, and that's what we should expect. Even though with a small number of rectangles, LRAM, RRAM, and MRAM might be quite different from one another, the more rectangles you have or subintervals you have, as you increase that number in, all 3 of those rectangular approximation methods converge to the same number. And in this case, you can probably see it. They're converging toward 9. The actual area in this case is 9. So here's one more example, and I'm going to save that for a new video so we can stretch this out just a little bit.